Testing 1 2. Test 1 2.
Should we move it? Might be difficult. I think it's just for the people up front. Just a minute or two.
Is it over?
Go ahead and give him some
Yeah, just a minute or two left. Test 1, 2. Cool. Yeah.
All right. Awesome. Good evening, everybody. Welcome to the Humanities Center at USD. This is such a special, highly anticipated occasion, and we're thrilled to have such a great crowd. So let's start by giving you all an applause for showing up. I'm Jesse Mills. I'm in the Ethnic Studies Department, and I work here in the Humanities Center in the capacity of collaborative research and also coordinating the Knapp Chair of Liberal Arts program. So it's been particularly thrilling to have the team, the research working group team in mathematics and art, architecture, and art history, and the and engineering school bring such an amazing program, and to have Martin and Erik with us for the week to just blow our minds with just thinking outside the box and just having a lot of fun with where our minds can lead us. So I just wanted to just provide you a brief welcome, and for those of you that aren't aware, the Knapp program, the Knapp Chair of Liberal Arts, was established in 1995 with a generous endowment from the estate of Mary and Churchill Knapp of La Jolla, California. And when you combine the Knapp program, which brings such amazing, internationally acclaimed scholars and lecturers and artists to our campus to really help us dive deeply into aspects of the humanities and liberal arts, to really invigorate our campus. I mean, this is just really special and very exciting. And the Illume Speaker Series, of which this is a part, is our effort to engage our scholars here on the campus, in our local community, and from around our artistic and scholarly fields to help us with our liberal arts learning and illumination. So that's basically all I wanted to do, was just provide a little context, a little bit of a warm welcome, because we're so grateful to have all the generations with us, engaging in play. If you haven't already had a chance to, we encourage you to look in the exhibition space in the gallery, where we have some of the mind-bending works of the Demaines. So without further ado, I would like to actually introduce my colleague in industrial engineering. I'm learning in industrial engineering. Odesma Dalrymple is an amazing colleague who will also help provide the introduction for Erik this evening. So thank you again for being here, and I hope you very much enjoy the lecture.
All right, thank you very much. So first of all, I want to acknowledge the team of collaborators that were sort of, as Perla said it, we were, I forgot what's the word that you used, Perla. You said we were scheming. So the co-schemers in sort of orchestrating this amazing week and bringing both Erik and Martin here. So Perla Myers from mathematics, Satya and David Dos also from mathematics, Daniel Lopez Perez, who was not able to be here with us today, but from art and architecture, and then myself. So it's been a real honor and privilege to be invited to be part of this team and to put together this amazing program. Usually I'd like to be able to speak more without sort of looking at my notes, but when you have such accomplished scholars, you feel like you have to make sure you get all of their accomplishments right. So I'm going to be sort of looking at my notes here, and I apologize for that. So I'm going to start with Erik, because I'm going to say that Martin is kind of partly here at USD as well, because he is now a research associate in the mathematics department. So we'll start with our true guest, and then we will move to describing a little bit more about Martin's background. So Erik's research interests range throughout algorithms, from data structures for improving web searches, to geometry of understanding how proteins fold, and then to computational difficulty of playing games. He received a MacArthur Fellowship as a computational geometer, tackling and solving difficult problems related to folding and bending. moving readily between the theoretical and the playful with a keen eye to revealing the former in the latter. He appears in the origami documentaries Between the Folds and Nova's The Origami Revolution. Now on to our Martin, we sit partly here as well. Martin is an artist and a mathematician. He's the Angelica and Barton Weller Artist in Residence at MIT. After studying glass blowing in England, he started the first private hot glass studio in Canada and has been called the father of Canadian glass. Martin's pieces from this period are represented in the permanent collection of major museums, including the Canadian Museum of Civilization and the National Gallery of Canada. He's a research, like I said, he's a research associate here at the mathematics department, and so we're really happy to have both of them. And I turn it over to Martin and Erik. Thank you.
Thanks everybody for coming. How many people were at our talk on Monday? You were there. I recognize you. Cool, so about half. There's going to be no overlap with Monday, except that in Monday's talk there was a theme of fonts, and we're going to continue that theme today. How many people here have used a font before? I hope everyone. How many people have designed a font before? Come on, guys. There've been a bunch of students here in a research group meeting every morning who've been working on designing various fonts, and I want to share with you a bunch of fonts that my dad and I have designed. Currently, I'll be the speaker, but maybe he'll jump in. We'll see. And there are a bunch of reasons to play with font design. One of them is having fun, and that's certainly our primary motivator. But another interesting one is it's a way to share mathematics and research in general with a broad audience. It's very accessible and hopefully fun to interact with and play with. And in particular, we're kind of targeting the people who like solving puzzles. So a couple of terms. I'm going to use the idea of a mathematical font, not to be like a font for writing equations, but a font that expresses mathematics by itself. So we're going to see a bunch of fonts like the one down here that are inspired by either theorems we've proved, or other people have proved, or open problems that we're still working on. And as I said, I think this is a great way to expose how neat and cool and beautiful mathematics can be with anyone who can read, I guess. That's the only prerequisite. And especially people who like solving puzzles, because a lot of our math fonts are puzzle fonts where, like this top image, it's not so readable by itself. But if I tell you the rules of the puzzle, you can try to solve this puzzle in order to decipher the text. This is actually the solution. The bottom is the solution to the top. And so the idea is that you engage the reader with the mathematics that you're interested in by having them solve puzzles in that mathematical world, and with the promise of secret messages. And I guess you could also write messages that only good puzzle solvers could read. So some bonus application. This is applied math here. So that's sort of the general spirit, and we've designed a whole bunch of fonts in. Most of these are mathematical and puzzle fonts. Some of them are just mathematical, some of them are just puzzle. I won't be talking about all of them. I'll be focusing in on these. So we're going to just go through one by one. I'll tell you about the related mathematics and show you the font, and we'll get to play and solve some puzzles and things like that. So the very first font we designed is based around this idea of hinged dissection. This is an old idea, over a century old. In particular, is this beautiful dissection cutting an equilateral triangle into 4 pieces, hinging them at points, and you can fold it into a square. So you could use this to build a table, and if, depending whether you have 2 people over or 3 people over, you can rearrange the table accordingly. So very cool, and this comes actually from the puzzle community. It's conjectured this is optimal. We don't know whether 4 pieces is optimal for this particular shape. So, but the open question is, can you do this for any 2 shapes? Can you always hinge dissect one shape into another of the same area? And we started working on this back in the late 90s, and we proved this nice result that if you have a shape that's made out of little repeating units, like unit squares are called polyominoes, or equilateral triangles or hexagons. Actually, any shape works for this theorem. Then there's one hinged dissection that will fold into all arrangements of n copies of that shape. So this guy has area 14, is that right? No, 12, can count, 3 times 4. There's one hinged dissection with 24 pieces that will fold into all polyominoes of area 12. So you could do 8 pieces will make all tetris pieces, and so on. And it's just, you take the squares, you divide them in half. You have these half squares, arrange them in a circular chain, and you can get any polyomino of the appropriate size. And there's similar results for all the others. So this seemed cool. And I guess I should point at polyobolos in particular, because this is the one we use for a font. So these are shapes made out of half squares. And it turns out if you subdivide into 1/4 of this shape by cutting here, you can also hinge dissect all of those. So we thought, okay, this is a neat theorem, but for people to really appreciate it, we need to make a font. This was actually our first, so we hadn't established this as a method for expressing mathematics, but this was a paper in Journal of Recreational Mathematics, so for fun. And we came up with a font where every letter has the same area, and it's made up out of half squares, so of course the same number of them. And so our theorem applies. So for example, the A over here is made up out of this many half squares. And so you subdivide each of these into 4, and you get this picture. So this is a hinged dissection of 128 pieces, if I recall correctly, that can fold from the letter A to the letter B to the letter C to the letter D, also to a square. We designed the area to be a square number. So that's kind of cool. And it can also make any shape made out of these pieces, but in particular every letter of the alphabet. And we can, we've sort of, sadly I don't have an animation of this. Let's go here. But you can write your favorite message in this font. Open problem is to animate it, I guess. And since this font, we actually sort of solved the mathematical problem. So at the time, this is more of an open problem. We wanted to know, okay, can we generalize to 3D? Turns out, yes, you can take a cube. If you take a bunch of cubes and hinge them in this particular pattern, repeat it n times, then you can make any shape made out of n cubes. We turn this into a sculpture. So this is an interactive sculpture. You put on the gloves, and you can rearrange this giant chain of blocks into any shape made out of somewhat extruded cubes here. And we've used it to build robots. So these are chain robots that have motors to execute the hinge dissection and can change from any shape to any shape. If this is a long enough thing, you could use this to build programmable matter like transformers or Terminator T-1000 robots that can change their shape from anything to anything. They're pretty tame at this point, but wait for the future. Maybe the technically coolest is this one where each unit is just 1 centimeter cubed. And we had to build some special motors to make it to work efficiently. This big robot on the other side is taller than I am. So this is practical. And it comes from that font design. And on the mathematical side, we can prove universality. So there's, given any finite collection of shapes, let's say in 2D, then polygons of the same area, there's one hinged chain of blocks that can fold into each of these shapes. And that was a big culmination of a lot of different folding and dissection results. So very exciting. Now problem solved. On to the next font, unless there are questions. Okay, so next font is, so this was a mathematical font, but it didn't really have a puzzle element. Next font is very puzzle heavy. This is an example of a puzzle. This has a secret message, which I'll reveal by the end of this section. And so, secret messages. And it's based on an open problem, which is still open. It's 17 years old, called the conveyor belt problem. So I give you a collection of disks in the plane, non-overlapping, and I give you a conveyor belt. And the disks aren't allowed to move. Think of them as like gears. I want to tightly wrap the gears with this rope. So the rope's not allowed to cross itself. It has to be taut everywhere. It can't have slack. And it has to touch every disk. So if I rotated one of these disks, every disk would turn. Is that always possible? That's not the open problem. The answer to that is no. There's a rather extreme example with 3 giant disks and 4 little tiny disks. And this cannot be wrapped in such a way. But it seems like to come up with a bad example like this, you need big disks and small disks. So the open problem that's still open is, can you do this if all the disks have the same size? So a bunch of unit disks in the plane, can I always wrap it in this way? Conjecture is yes, but it's been open for a very long time. So this is a frustrating problem. We worked on it. We got stuck. So instead, we made a font. We started, this is with Belen Pellup. We started with thumbtacks and rubber bands, which was fun. And we would pose it as a puzzle to each other, like put down some thumbtacks and then give it to the other co-author. And it's like, oh, it's an A. And then, can solve it. So this was a lot of fun. And this is the full font. On the left is the solved version. That's if you don't want to communicate your message secretly. On the right is the puzzle version. So each thing on the right, they don't have unique solutions, but the idea is they have a unique solution that is a letter. So if you are told that this is a font, then you can solve each puzzle here and figure out that, oh, it's A, then B, then C. So let's do a quick example. So, I mean, if you look at the text up there, you're going to know the answer. Here's USD, and when you solve it, that's what it looks like. But I have some more here that I don't have to type. So here is the original puzzle, which I'll be impressed if you can solve it at this point. This is kind of a big ask, but can you read any of the letters here? C-O, maybe. Conveyor, oh, that's good. There is a conveyor somewhere in that sentence. Convey, very good. This is convey. This is conveyor. Oh, via, yeah, very good. All right, convey via conveyor belts. Sort of meta. I have a few such meta prints here that we designed. So this is, I am wondering about a book, and we start to lose some of the contents here, where the dots are randomly colored. And you see they're randomly colored. And even more self-referential, this is a statement of the open problem, or a variation of the open problem in the problem itself. So imagine text made up of dots. The dots are wheels with elastic belts wrapped around them to create letters. Stretch your imagination. What if some of the belts are missing? Is there an algorithm to find them? So this is sort of the algorithmic version of the problem, and with less and less of the letters explicitly written down. So you've got to solve more and more to read the puzzle. So that was conveyor belt font, puzzle font. Clearly also mathematical, still open. Next up is linkage font. This is, oh, I think there's something wrong with the projector. OK, there we go. So this is, again, a puzzle font, and it's inspired by protein folding. Maybe that was a hint. So here's the meta puzzle for you is, what do these 4 polygonal chains have in common? There are 3 or 4 things they have in common, so shout them out. Number of joints, good. They each have 1, 2, 3, 4, 5 joints, 4 links. There's so the yellow is just to indicate which is like the beginning of the chain. But yeah, they each have an indicator for the beginning. Then red endpoints, extra. We'll see why we want to distinguish the endpoints later. Yeah. The same angles, yeah. So like first you have a 90-degree angle. Now some of them turn left with that 90-degree angle. Some of them turn right, but they both start with a 90-degree. Then they have a like 120. Then they have a 180. So they share the same angle sequence. Yeah. They also have the same distance. In fact, not only are these 4 distances the same, but all of the distances are the same. They're all a unit length. Each of these 4 links are the same. I think that's all they have in common. They're also all 2-dimensional, but and these are all the ways actually to draw this chain subject to those constraints with the same lengths. If I pin the yellow thing as horizontal, then you can go left or right with the first turn. You can go left or right with the second turn. That's the left and right dichotomy. And this one can only go straight because it's held fixed at a 180-degree angle. So this is motivated by how proteins fold. The backbone of a protein or a DNA molecule has roughly fixed edge lengths. They're roughly all about the same, maybe within 10 or 20%. We're going to idealize that to the same length. And the angles are relatively fixed. And so how can we turn this into a font? First let me tell you some of the related mathematics. This world is called fixed angle linkages. Linkage means that the edge lengths are held fixed, and fixed angle means the angles are held fixed. And one of the main areas of research is thinking about flat states, which seem to play some kind of role in biology. So first question is, if I give you one of these fixed angle chains, can you flatten it at all in the plane into 2D? And it turns out that is NP hard, which means computationally intractable. And then the next question is, if I give you 2 flat states of one of these chains, can you reconfigure from one into the other through 3 dimensions without collisions? This is called flat state connectivity. And there's some nice results, like if you have an orthogonal chain where all the angles are 90 degrees, then you can just kind of pick it up one link at a time and get a nice canonical zigzag, kind of like a helical configuration, and reconfigure from any chain to any other. But still interesting open problems. I'm getting a little technical, so let's go back to the font. So here's our font. This is also on my business card. I write my name. So this is in the solved configuration. But each of these, and there's a little bit of notation, like let's take E for Eric. So we've got a 90-degree angle, then another 90-degree angle, then a full turnaround. So this doubled edge means there's 2 edges on top of there, then a 90-degree angle, then a 90-degree angle. And that is the description of an E. And it doesn't have to be drawn this way. It could be drawn in a bunch of other ways. So for example, here's the letter G and all of the configurations that have the same length and angle sequence as the G. But you can see only one of them looks like a letter. So this communicates a G just as well as that does in a puzzle sense. Ideally, I'd give you a physical version of this, and you can flip, 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 and try to find where it's the letter G, that it is the letter G. And that's the angle sequence at the top. How did we check that this font is what we want it to do? We drew all of the different foldings of all of our letter designs and stared at them and looked at whether any of them were letters that we did not intend, but luckily just the yellow highlighted ones are correct. And so we've got our font, uniquely encodes some things. So here's some puzzles. Can you read any of these words? Folding? Very good. Yeah, this is folding. Hello. Nice. So computer scientists should know what this is. World. Yeah. I don't know how you'd read it, but given hello, you conclude world. This is an L, definitely. Nice. Any other letters or words? Fun. Yes, this is fun. Nice. You should. You have fun. Yep. Very good. Any guesses what comes before folding? Protein. Yeah. So you could do a certain amount of guesswork and also pattern matching and so on. But this is definitely a challenging font to read. Protein folding. Hello world. Have fun. Cool. Any questions about linkages? We're going to take this idea of folding linkages into a more puzzle domain in a moment. Yeah, question?
So you just give your students or like office workers like this STEM and then just try to solve it to different letters?
How did we find these, is the question, or?
Yeah, like, I mean, like, how the puzzle goes.
Yeah, well, so we designed these letters by hand, the two of us, and then we wrote a program to do all this enumeration for what you can fold it into. So again, we can take like USD, and the computer constructs a variation of how you can fold that linkage by flipping the joints randomly. You can tweak the randomization until you find something that looks sufficiently difficult, and then present this to someone, and they can figure out that that is USD. Yeah?
In your program, is there a infinite random, like does your program infinitely randomize the letters? Because there's still a limitation. It's not like USD has infinitely many.
Yeah, right. There's only 2 to the 5 or so different ways to fold each letter. So it's pretty limited because we're restricting to flat configurations. If you went into 3D, then you would have full continuum, like R to the 4th or whatever different configurations. But here it's just 2 to the 4 different configurations. So, yeah. Another question?
Yeah, I have a question. Does that tell us something about math, or does that tell us something about the Western alphabet? Because did you try it with Arabic?
Interesting. So I guess you're saying that the fact that this works with, I forget, is it length 6 chains with some angles is enough to express all of English? Is that specific to the alphabet? Probably to some extent, although most alphabets have roughly the same length. But we haven't tried it with other alphabets. And a lot of our fonts work best, I would say, with connected letters that are connected. And so Chinese and Japanese would be pretty difficult. But let's see, maybe at the end I can show you, for the conveyor belt font, there is a Japanese version. And despite the connectivity limitation, that is possible. But we focus mostly on English alphabet because it's the one that the two of us are really good at recognizing. So we know when we have a letter that looks good. The other alphabets are harder for us. So. But we encourage all of you to take your your native alphabets and adapt these fonts or come up with your own fonts. We don't want to be the sole keepers of font design. Please join us in this project. But yeah, I think that's a fascinating question, how specific to the English alphabet this is. But it's hard to know the answers to that question until we have more experience. Other questions?
Does this work for characters too? Like if
emoji? All of Unicode? Yeah, Chinese, as I was saying, with disconnected letters are a lot harder, I think, to communicate with. I mean, especially linkages are going to be connected, conveyor belts are going to be connected. But it still may be possible.
Did you use an algorithm to design your Super Mario shirt?
I wish I designed this shirt, but sadly I bought it, or it was a gift. So I don't know who designed it. Maybe Nintendo? Okay, we're going to move on to another closely related font, also in kind of linkage, fixed angle linkage world, but represented by this toy. I don't know if you've ever played with this toy called Tangle. It's a lot of fun. The inventor, Richard Zavitz, has used it to make beautiful sculptures and all sorts of cool things. But fundamentally, it works like a unit length 90-degree fixed angle chain, but with slightly rounded corners. So here are some examples of things you can do with this puzzle. I could take this highlighted red region and flip it around. So I'm always preserving these 90-degree angles that are not actually drawn, but rounded. So that's one kind of flip you could do. Here's another kind of flip you could do. And these are not all the things you can do with this puzzle, but this was an established move set for reconfiguring a tangle. This is a more complicated one where I fixed the black, or maybe in this picture I fixed the green, let's say. I pick up the black out of the plane and drop it back down using these as pivots. This is called a translation move because the black translates from one spot to another. Here we're doing a reflection. So a problem that was open until a couple of years ago is, are these moves enough to reconfigure any flat state of a tangle to any other? Sadly, the answer is no, but it's not obviously no. Most configurations seem to work. These are some configurations that have none of these moves, and so they're rigid. There's no way to reconfigure one of them into another. So this was, a small result, so we wanted to beef it up a little bit, and so we designed a font, actually 2 fonts. So these are, each of these letters is made out of the same tangle, meaning exactly the same length of this thing. So whereas in the linkage font, we were changing the angles and using that to express the letters, here it's actually the same object, and it can be folded into each of the letters. And we did 2 of 2 different sizes, and they're kind of fun. And let me show you let's write our favorite message, USD, and in one font or the other. Now, a natural question is, can I actually reconfigure the U into the S into the D without collisions using the moves that I told you? Probably the answer is yes, but we don't know for certain. Here's one example of reconfiguring our letter R with these are photographs of a real tangle, into the letter Z. And probably you can go between any pair, but we don't know for sure. So that was tangles, yeah. Is 52 the minimum number to express English? I don't know. So, I mean, there are a lot of aesthetic choices here, and I think the best way to answer that is to try by yourself. I think it should be a multiple of 4 in order to have a flat state. So you could try 48 and so on. I'm guessing you need more than 4. So it's somewhere between, the right answer is somewhere between 4 and 52. And there's maybe no true answer because, I mean, you could maybe go lower, but it looks kind of like English. But I'll bet you could go lower than 52. Open problem. Cool. Next font is a Juggling Font. So let me tell you a little bit about the mathematics of juggling with these handy juggling balls that we get provided every morning. Here is a mathematical notation for expressing juggling patterns. Doesn't express everything about a juggling pattern, but it's very useful. So the idea is you draw a picture. You assume that the juggler is going to alternate between throwing with the right hand, left hand, right hand, left hand, right hand, left hand, right hand, left hand. And so the left hand is blue, the right hand is red. R for red, L for blue. Some L in there somewhere. And you draw an arrow saying, so assume that every hand, when it has a ball, throws it. Then when will that ball land? Okay. In the regular juggling pattern, which I was just demoing, every time you throw to 3 time units into the future. That's because there's 3 balls. It always alternates hands. It goes from blue to red, red to blue, and so on. And so that is the regular 3-ball juggling pattern. We represent that by the number 3. Amazing. But just to imagine how this pattern works in general with 2 hands, but different numbers. The number 1 represents this juggling pattern where you immediately throw 1 ball from the right hand to the left hand, and every time step you're throwing the same ball to the other hand. So that's this picture. You get a path graph. The 2 juggling pattern is like this, or if you like, it's like this, where every time you throw, the ball is going back to the same hand, and so nothing really interesting is happening. So usually jugglers use the number 2 to say, just hold on to the ball for 1 time step. Don't do anything with it. And I guess we can do 4. I haven't tried it with oranges, especially open oranges. 4 looks something like that. Okay, so those are regular juggling patterns, but you can express huge, like infinite variety of juggling patterns with this notation. So for example, this is one of my favorite site-swappable expressible patterns, which looks like this. Amazed I haven't dropped yet. I probably just jinxed myself. This is called 441, and it means you throw, the first 2 throws go 4 time steps in the future, then the 3rd throw goes 1 time step into the future, and then you cycle through. So you do 441, 441, 441. It's 44, well, sorry. I don't know. I just do it. But you can see the horizontal throw, that's the 1, and then the up throws are force. And it's really hard to see this picture, but it's easier to see the animation. Now, I don't want to lead too much into fonts, but I would like to say this expresses kind of like the letter U, right? You've got a vertical thing going on over here, and some horizontal thing going on over here. So that's going to be the idea of the juggling font. Let me first mention that there's a lot of stuff in juggling patterns that is not expressed by site swap notation. So this is a pattern called Mills Mess, and it's distinctive because it involves your hands crossing. But from a site swap notation, if you look at which ball is going to what hand, it is just 3, 3, 3, 3. It's identical to regular 3-ball juggling. So notation isn't everything, but that's a little bit about the mathematics of juggling patterns. And site swap notation has been used to design all sorts of new juggling patterns. I think 441 was new after the invention of this notation. Anyway, we made 26 juggling patterns, one for each letter of the alphabet. And so you see the animations, and then above the animations is the trace of all the balls, where they go. It's just this animation, all of the frames superimposed on top of each other. And hopefully they look mostly like the letters of the alphabet. There are a few liberties taken. It's really hard to make a B that stands upright. So we've let it fall over 90 degrees. So it's very hard to make a letter B that's where one thing stands on top of the other. So instead we make a letter B that's been rotated 90 degrees. So it's like standing on its side. Get the animations going again. Letter C is also rotated 90 degrees. Letter E is also rotated 90 degrees. But you get used to it. I think you could express some pretty interesting words this way. Another question? How many of these can I do? Maybe half. Some of them, like the letter S, I'm not sure anyone could do. Maybe. I think I've seen one person try. So it was a good challenge to try all these juggling patterns.
Whether it was a birthday present?
I don't think so. A lot of these juggling patterns are well-known juggling patterns. They have names in a certain sense, but a lot of them are just some version of 4-2 in this juggling notation. So let's write something. Here's text. We can write USD. So I don't know if there are 3 jugglers here, but we could do this one. If someone is willing to do the S, maybe not. Let's see. I don't have any of these memorized at the moment. So I'm not sure I could do any of these right now. But U is it's called box.
Can you do the S?
No, I can't do the S. But maybe the U is probably something like that. Yeah, it's been a while since I've done box, but you get the idea. Is it synchronous? No. There we go. That's something like the U. Okay, so this is a much harder version of something like 441, but this is synchronous, so you can't use regular site swap notation too. Meaning both hands are, well, no, anyway. It's a fun trick. One of the early ones I learned.
Oh my gosh.
So that's Juggling Font. Onward, maybe I will mention, both of these 2 fonts were prepared for Ron Graham's 90th birthday. Ron Graham is a famous mathematician, but also a famous juggler, and also studied card shuffling. So this next one, if you read right at the top, it says shuffle. So this is based on a rather advanced magic trick, which I cannot perform, called Faro shuffles, perfect shuffles, where you take a deck, use, let's say, 8 cards for now, just to make the figures easy to draw. You split it exactly in half, so you have to cut right in the middle. That's one of the harder parts. Then you fan one of the one half of the cards 1-to-1 with the other half of the cards. Easy. It's like a riffle shuffle, but where you get exactly left, right, left, right, left, right. Actually, 2 ways to do this. You could have, if A is your top card, you could keep A on top. That's called an out shuffle because the outer cards, A and H, remain on the outside, A and H. Or you could put A below E here. And then you have in shuffle, and the outer cards, A and H, go in one, here and here. So there's 2 perfect shuffles for a given deck of cards. So as you imagine, you might be able to rearrange the cards in different patterns, different permutations, by mixing up these 2 shuffles. Maybe most famously is that if you take a regular 52 card deck and you do 8 out perfect shuffles, then they return to their original order. So if you have a really good magician, you can take a deck, shuffle it 8 times, and so look, you imagine after 8 shuffles, totally random. But in fact, it is exactly how it started. So you can have a perfectly sorted deck if you started that way. You just need to do this perfectly 8 times. Imperfect shuffles for 52 cards are not as interesting. You end up back in your original order after doing it 52 times. I don't think anyone would last that long. But for a small number of cards, that could be interesting. And so that's for 52 cards. But there's this general sequence for if you have 6 cards, then you need to do 4 out perfect shuffles to return them to the original order, or 8 cards, 3, and so on. And this is understood, although I think it's an open problem to completely identify this sequence. But for all small values, we know the answer. And one of the key papers in this topic is by Diaconis, Graham, and Cantor. And it characterizes, if you mix in and out perfect shuffles, exactly what permutations of the cards you can get. It's a group. It's a pretty big group. It's of exponential size, but it's not everything. So when you do perfect shuffles, for example, the top card and the bottom card always remain kind of paired up. They might move closer to the center. They might switch like this. But they always remain the same distance from the center as each other. And that's true for all pairs of cards initially paired up in this way. And that's sort of the main restriction on how you can permute the cards. OK, how do we turn this into a magic trick? One of the classic ways from the 50s is called Elmsley's trick. You can guess who invented it. And it's a very cute trick. You can all try this at home once you learn how to do perfect shuffles. So if you have n cards with exactly log base 2 of n shuffles, you can get any card you want to the top of the deck. Gotta get this right. Top, bottom? Sorry, the reverse. So if I have, so suppose you get somebody to choose a card, you have them put it on the top of the deck, and now you do a sequence of log n shuffles. You can take that top card and move it to any position you want in the deck. Maybe you want it exactly in the middle, because if you can do perfect shuffles, you can also do perfect cuts. And so you can take somebody's card on the top, get it exactly to the middle, and then with one cut, you reveal their card. And they're like, wow, you just shuffled the deck. How did you do that? And so here's how you do it. It's very simple. You take the position you want to put the card in and write it in binary. So maybe you want it to be the 6th position from the top. 6 is 110 in binary. And then you do 3 moves. Wherever there's a 1, you do an in perfect shuffle. Wherever there's a 0, you do an out perfect shuffle. It's like the easiest translation you could imagine. It takes some thinking to realize that this works, but it's also not hard to see. So that will do that trick. Now, what about the inverse, which is what I originally said mistakenly? Suppose I want to do in and out perfect shuffles, and I want to take some card from the middle of the deck and move it to the top. So exactly the reverse. Maybe I get someone to pick their card, I do a perfect cut, I have them put the card in the middle, I close the deck, and then I do some shuffles, and then magically their card is on the top. So that would be the effect here. This was an open problem for like 50 years, and finally Diaconis and Graham solved it. And they have a little algorithm for how to do it, which I won't go into. It's a little bit complicated. Although a fun thing is that this algorithm literally had never been implemented. And so in designing a font, which I'll talk about in a moment, we found a tiny typo and is now fixed. So we saved mathematics thanks to font design. So how do we turn this into a font? Well, 26 cards. You can buy these decks online, alphabet decks A through Z. And now we're just going to do a sequence of perfect shuffle. So we might start with the cards in sorted order. And then we'll do a sequence like inside, outside, inside, inside. And now we're going to bring whatever next letter in the alphabet to the top of the deck. So here we have A, B, C, D. Let's try USD. And maybe if I go a little like this, it'll get bigger. So you see in the bold setting here, we have U, S, and D. In between, we do a sequence of up to 5 perfect shuffles. 5 is ceiling of log base 2 of 26. So at most 5 shuffles, you can get any card you want to move it to the top. Now this is a bit funny. You see here, to write a U requires 5 perfect shuffles. Then, given this order, to write an S requires 3. But if I wrote just S, it ends up taking 5 moves. So how you write a message, it's no like single answer for each letter. It depends how you've messed up your cards so far, because you don't want to like resort your cards in between each letter. So if you were to perform this trick, which again I can't do, it would look like this. So you start with a perfectly sorted deck. You do an inside perfect shuffle. You do an outside perfect shuffle. You do an outside perfect shuffle. And inside. And inside. And there you've got the letter U. Amazing. Then let's do maybe 3 more. You do an inside perfect shuffle, and you do an outside perfect shuffle, and then you do an inside perfect shuffle, and you've got the letter S. And if you keep going, you'll get the letter D. So you can impress all your friends with that trick. Yeah. Cool. So any questions about card shuffling?
So that one isn't just like a font in the way that you can
This is
some code and has to be your R.
Right. Yeah. So this font is fun because it's, I would say, context sensitive. The way you write the letter F depends on what all the previous letters you have written are. So it's a very non-traditional font. I doubt you could write this as a true type font or any existing font standard. That's why we write custom software to render all of our fonts. It's also not the most beautiful font as like a visual depiction in 2D. It's really meant to be performed. But then that takes a long time. So, I think the fun way to write this font, which I kind of skipped over, is a pattern like this. This is your secret message. You write I-O-I-I-I-I-I, I-O-O-I-I, and that encodes ABC. If you have to be told when to look at the top card, and so you could figure this out by, I mean, manually, doing perfect shuffles is hard, but the easy way is to just do card, 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 card. So you could execute this and then discover the secret message.
It looks like Morse code.
It's kind of like Morse code, yeah.
Is the sequence unique?
The sequence is not unique. That's a good question. Even if I ask for, I'm trying to remember whether the shortest sequence is unique. I don't think so. Definitely, if you say that the sequence of moves should be at most log n steps, there are typically 2 solutions. Maybe some of them are unique from a given position, but some of them have 2. It's because of the ceiling business. If it was exactly log n, like if you had the number of cards as a power of 2, it would be unique given that constraint. But because it's not perfect power of 2, we end up with ambiguous solutions, and the software just chooses the shortest one.
But if I gave you like a large number, you could turn it into binary and then make the message out.
Yeah. Oh, I see. Like this is just a big binary number. You need to decide when to put these vertical bars. So in some sense, it's ternary. Yeah. So it's not quite perfect. It's not just a number, but well, I guess you could write it in ternary, and then cool. Yeah, good idea. Okay, next font, Voronoi font. If you were at our 2-minute presentation yesterday, anyone there? Okay. One person. So you see this slide. Marty and I gave it simultaneously 2 conversations. I'll spare you from that this time. So Voronoi diagram is a very old concept. It was definitely not invented by Voronoi, but he's one of the more recent people to invent it. Descartes drew this diagram, which has various stars. And the general idea of the Voronoi diagram is you start with a set of points, say, and you imagine growing a disk from each point. And where those disks meet each other, that purple line is the Voronoi diagram. And so that's what's going on here. You've got various points, and they're creating these circles, and then these straight lines in between, that's the Voronoi diagram. And they appear all over the place. They're used a lot in geometry. They're used a lot they arise naturally in biology a lot, like the pattern on a giraffe or a jaguar, or these are all Voronoi diagrams because of a natural process. The galaxies in the universe seem to form a Voronoi diagram in 3D. Lots of cool things. You can make fun art. These were some early experiments that my dad and I did, making like stained glass. So this is technically a maze. And one of the colors, I think, black. And here's some beautiful Voronoi art by Craig Kaplan, a former classmate of mine, now a professor at Waterloo. And these are a couple other examples, Voronoi fractals, taking an image and representing it using a Voronoi diagram. So they look cool. So we thought we would make a font. It's quite challenging. It's a little hard to appreciate without playing with Voronoi diagrams. So let me play with one. So here we have some letters. Let's take our favorite message, USD, and blow it up. And, oops, sorry. Mice are hard. And let's do draggable. So I'm going to drag these points around, and you'll get a feel for what a Voronoi diagram does. So usually what happens with the Voronoi diagram is you get 3 perpendicular bisectors meeting. And that's not very conducive to drawing letters. So the challenge here is to get these points, let's see if I can remember where this one was, somewhere around here, to look like letters at all. It's quite hard. And to help us out, in general, the Voronoi diagram has these rays that go off to infinity. So those we draw slightly differently from the finite ones that live in here. And that, because if you had all of this black, it wouldn't look super much like an S or a U or a D. But with that extra embellishment, we can get some pretty nice looking letters. Now, of course, the puzzle here is I just give you the points, and you have to figure out the letters. Which, I mean, you sit there and you draw perpendicular bisectors, and it takes a while. But if you printed this out, I think you could construct a Voronoi diagram pretty well, and you would discover the secret message, USD. It's also fun to just look at the Voronoi diagrams, maybe a little more readable. OK, so far so good. Let me switch to here. So this is a second font in this series. This is a Voronoi diagram. I claim it represents USD. Can you imagine why? The dots, yeah, exactly. So the dots are in the pattern USD. And in this case, as a puzzle, you'd just be given the Voronoi diagram. You have to reconstruct the dots. Turns out that's a big mathematical problem that's been studied. References are on this webpage. And so you can find the dots that generate that Voronoi diagram, and then you would decipher the letters. That's a bit trickier to do in person, but it's a good puzzle. So this is the full alphabet in puzzle form. This is in the Voronoi inverse form, and that's with the points. So fun stuff. One more font, one of the most recent and one of the coolest. So maybe you've made string art before. You take pins on a board and then connect strings, maybe with different colors, to make some cool thing. Hey, look, here's a font. So this is one way to make a font, but we wanted to find a more challenging way, more mathematical way. And we saw this video by Petros Vrelis in Greece, and it is mind-blowing. Wait for it. So here he is. He has a simple, I think, 200-pin bicycle wheel, and 1 really long string. It's easy to get really long strings. And it's going to accelerate. Black string, white background.
He really does move that fast.
Yeah, he's super fast. Jesus Christ. Literally. That was probably about 4,000 or 5,000 line segments.
That's a very long string.
What was the question?
Was string art alone, just with this string?
Just string. That's just the string you're seeing. We'll zoom in now, because you asked. This is in the video. So it's a ton of string. I mean, this is probably not the first work he made. I think he tried it a few times before he committed to recording the video. As you can imagine, this takes many hours to make, and he did it over a period of, I think, a week, this video. It's pretty crazy, right? So we saw this and like, wow, let's make a font. So here's some more examples of his artwork, which these are some of these are for sale. And so we made a font in this style using his algorithm. So as you might imagine, he does not, whoa, cool. He does not do this by hand. I mean, he makes them by hand, but he doesn't design it by hand. There's no way you know to go from here to there first. This is an algorithm that tells you for a given target image, it tries to find the best way to represent that image using just black string on a white background. And so it turns out that algorithm could also make every letter of the alphabet. And this is one of the few examples where we also went, we made lowercase letters. Question?
So when he's doing that, when he's moving the string around, I can't see any of the keys or anything to tell him,
Oh, how does he do it personally? Is that a secret? Do you know?
I think it's a secret.
Yeah, he's using the output of the computer to tell him where to go. I'll leave it at that. So why don't we just zoom all the way in here? So you can see the individual strings, and they form the letters. That is letter U, letter S. Let's animate one, shall we?
You can actually style the letters differently with this too, right?
Yeah, I mean, this one you could really write probably any letter in any alphabet. Maybe. I think this is Arial. We did find some fonts worked better than others, and this outline font worked a lot better than like a solid. So there are some limitations. You cannot make everything with this technique, but these letters work really well. Yeah. The algorithm is secret. Sorry.
Is there a, can you minimize the number of pins?
Good question. So we worked on that very problem. So this one has, I think, 200 pins, and every one is 1,500 strands. But before that, we had already worked on a font in this topic, my dad and I, and so we put these together. So this is not necessarily minimal, but much smaller. So here we have A through V, that's 20-something pins. In this case, they're in a rectangular pattern, which is quite restrictive. And we came up with ways to make all the letters of the alphabet. So this would be like this is much easier to try at home, and you can do it. There's a couple of variations. I don't know if you can tell the difference between those letters, but one set is Eulerian. It's possible with one single tour to visit everything, and the other is none of the letters are Eulerian. And so a kind of puzzle for you to play with would be, let's go back to something like this. So here I've chosen, randomly, each one is either Eulerian or not, and your puzzle is to figure out which ones are Eulerian and which ones aren't. And if you hit randomize, you get a new series of puzzles accordingly. Other questions? Yeah, definitely the 1,500 is prettier. Yeah.
Have you tried other shapes? So you were showing us a rectangle and a circle. Have you thought about changing the shapes?
That's a good question. What about, I mean, you could try this algorithm with a rectangle. I think that would probably work fine. I mean, the main idea here is to use a convex shape. That makes it quite challenging, but you could certainly try other shapes. These are the only two that we've experimented with. And this you could definitely try to generalize to other alphabets. We just haven't done it yet. Maybe arbitrary emoji, Unicode. So I think those are the fonts that I wanted to talk about today. There are others. You can go to this website to play with them all. All the code software that I was demoing, you can play with right there. I talked about a couple of these on Monday. I think all of these 3. So this is a font where you take a square of paper, fold, flat, make one straight cut, and you can make any letter of the alphabet. This is a font that a bunch of students have been playing with this week. I think there's an example of USD in that room right over there, where you take one strip of paper and fold it just along 90 and 45-degree creases, and you can make any sequence of letters out of one strip of paper. This is folding a maze out of a really big rectangle of paper, all with a bunch of creases. There's some glass blowing fonts, and there's some more that we're working on this week and coming soon. So refresh this page every day and see if there are any new fonts. Every few months or so, we come up with another one and post it there. Thanks. More questions? Had a lot throughout, but anything else? Or more font ideas? If you've got a cool math or CS result that you think could be turned into a font, please talk to us and let's collaborate. And thanks for coming. And don't forget to check out the exhibit in here. There are a couple of font-related things and also computational origami-related things. And a few examples of what the students have been making this week while we're here, a lot of which is in the font spirit. Cool. Thank you.